This is 5-Minute Photovoltaics with Tim Rieblitz, brought to you by Quest at Arizona State University. In this video, we cover a brief intro to solar cell fundamentals. Solar cells in 30 seconds. This is a very high-level look at solar cell fundamentals. First of all, the sun radiates photons. These photons are harvestable packets of energy. Photons with enough energy can kick an electron from an atom's valence band, EV, to the conduction band, EC. This is the photoelectric effect. Electrons in the conduction band can contribute to current. So the overall name of the game of solar cells is to capture as many photons as possible and collect as many photo-generated electrons as possible. Harvestable packets of energy. In the formula on the left, E equals hc over lambda, we see that the energy of each photon is inversely proportional to its wavelength. So the shorter the wavelength, the more energy the photon has. The plot in the middle shows the power from the sun as a function of photon wavelength. The sun does in fact radiate a lot of power beyond the visible light spectrum. Photons in the blue or violet have a short wavelength and more energy. Photons in the red or infrared have a longer wavelength and thus less energy. The chart on the right reminds you of other forms of electromagnetic radiation, such as gamma rays, X-rays, and radio waves, and how their wavelengths compare to visible light. The photoelectric effect. Discovery of this law is what earned Einstein his Nobel Prize. This simple band diagram provides a visual of the photoelectric effect. If a photon's energy is less than the difference between the solar cell material's conduction band and valence band, no conduction electron can be generated. If a photon's energy is greater than or equal to this band gap, then a conduction electron is generated. When a photon's energy is greater than this band gap, the excess energy is lost to thermal processes generating heat. Optical absorption. In typical solar cells, to capture as many photons as possible, we use two methods: texturing and anti-reflection coatings. A flat silicon wafer will reflect about 30% of light. That's a lot of lost potential power. By texturing the surface in a chemical bath, such as diluted potassium hydroxide, we can form small pyramids on the surface. The shape of the pyramids increases the chance that a photon will be absorbed into the cell. The textured surface lowers the reflection to about 10%, depending on the photon's wavelength. Anti-reflection coatings are designed with a thickness and dielectric constant such that the wavelength in the silicon nitride is 1/4 of the photon's wavelength in air. This results in interference effects that result in maximum optical absorption. Combining the effects of texturing and anti-reflection coatings, we get reflectance less than 2%, again depending on wavelength. Electron collection. Solar cells need to collect as many electrons as possible. Here we can look at the various factors that govern solar cell efficiency and their design trade-offs. The efficiency of the solar cell is the ratio of the collected electrical power divided by the incident power from the sun. The collected electrical power is the product of VOC, the open circuit voltage, ISC, the short circuit current, and the fill factor. With VOC and ISC, we see a trade-off with EG, the band gap. In common, we see that we want to increase Ln and Lp. These are the diffusion lengths for electrons and holes. We'll cover this in a little more detail in a moment. Also for VOC and ISC, we want to minimize SR, that is surface recombination. For ISC, we also see that we want to minimize reflectance. We covered that just a minute ago. On the right, we see a cross-section schematic of a typical solar cell, including the various resistances that can contribute to series resistance. Using a highly conductive material for the fingers and bus bars, such as silver, allows for a low series resistance. So L, the diffusion length, is, again, something we want to maximize. It tells us how far an electron can travel in the solar cell until it recombines with a hole in the valence band. L is the square root of D, the diffusion coefficient, and tau, the total effective lifetime. Here we briefly describe the total effective lifetime. It is related to the lifetimes of three recombination mechanisms: Auger, radiative, and SRH, or Shockley-Reed-Hall. Auger is a process that dominates when there is a very high number of electrons and holes. It results in a release of heat through phonons. Radiative is a recombination process that results in the release of a photon with an energy equal to the band gap. SRH is another process that results in release of heat through phonons. Typically, this involves recombination with a defect in the material, for an example, an atom of iron. This was 5-Minute Photovoltaics with a brief intro to solar cell fundamentals. You can learn more at pveducation.org/pvcd-rom. Thank you.